Start recording. Let's spend some time today talking about the idea of refraction. Now, before we start anything, refraction is different than reflection. They're different words. Look at the spelling of the word, please. Make sure you understand that it's a different word. They sound similar. So I will emphasize the things I'm saying. So I'm going to say refraction, not reflection. Mainly today is about refraction, but we will talk about reflection at some point in time as well. Now, here's the idea behind refraction. When light travels through a given medium, such as air, it travels in rays that are somewhat, or we could say at least for the sake of Earth, parallel to one another. When those light rays hit another surface that is transparent, okay, the light rays bend. So when light hits water, how many people have been in a pool in the summertime, or somewhere near a pool, or clear water, right? And you look in the water from outside the pool and you see someone's body and it's like shifted over, like maybe an inch. You ever do that before? Ever notice this? I'll pull up an image of it in a minute. So imagine you're standing in the water. If you look from the outside, the person's body under the water will look like it's right here, and then it will kind of be staggered to the rest of their body. And what you're seeing is you're seeing the light being refracted in the water. The light is bent. It's bent to the side. So you literally see the person's body shifted over in the water. So when we talk about the bending of light, here, we're going to be talking about when light travels through different medium, or different media, I guess the plural mediums. So let's take a look real quick at this. So what do you see?
A cup inside a cup.
A cup inside a cup. All right. A beaker inside a beaker. A glass inside a glass. Fine. So what I'm going to do is actually pour some vegetable oil in here. And what I want you to do is just watch what happens, and then come up with some hypotheses of what it could be causing this, I guess. So I'm going to fill this one first, all right? So I start by filling the inner cup. You can still see everything, right? It's filled. Okay? Now, watch what happens when I go, you need to watch, guys. Look up, please. Watch it happen. This is actually kind of cool. So as I continue to fill this, and it overflows, what happened to the bottom half of that inner beaker? Where did the bottom half of the inner beaker? It's literally gone. Like you cannot see the bottom half of that. Right? Vegetable oil you can see through. I can see through it, so it's not like it's doing that. But for some reason, you can't see the bottom half of the beaker. If I do this, watch this now, right? If I fill it up continuously at the top, you're going to see it just... There we go. It's pretty cool, isn't it? I think it's really cool. It's the first time I've ever done it. I've seen this before. I've noticed it. I've never tried it. Alright, so let me explain what's going on. Now, what's cool is you can still see the inner beaker. See the white writing here? The blue writing is on the outer beaker. This blue writing. The white writing there is on the inner beaker. You can kind of see it from my hand behind it, probably, right? So it's still there. Now, I'm going to come around and let you look from above. So look from above, please. So try and get above here and look down. You can see it when you look from above. Do you see it? Okay, I want you to see it. You're going to see a little halo, or like a little circular shape around it. It's there. It just looks like it's invisible. Think about cloning, by the way. Anybody that's into like video games or like even like military applications, cloning, not cloning, what's the word? Cloaking, yeah. I'm thinking of Halo, that's fine. When you put like some sort of invisibility idea, or the fabric to change to support what's behind it. So look from above. You can kind of see from above, right? Look from directly above. Yeah. You can still kind of see the outline from above. It's like a little bit of like a shadow, if you will. Yeah. See like an angle. You kind of see it, right? Take a look from above. See it. See it? You kind of see a little halo in the shadow. So, the beaker has completely disappeared, and what will happen, obviously, is when I pour the liquid back out, you're obviously going to be able to see it. You're going to see it starting to show up right there. And again, you'll see that the part that's submerged in oil is completely gone. So let's figure out why this is happening. That's really like, our motivation for this lesson. Let's figure out what's actually going on that's causing this to occur. Any guesses? Any guesses?
Is it because since it's oil, like the light is being refracted more than it would be in water?
It definitely has to do with the fact that it's oil and not water. Absolutely. Because if I put water in there, it would not work. I should do that next year. I'll do one with water, one with oil. It definitely has to do with the fact that it's oil. Something about the oil. What did I talk about? What is refraction really? What did I say is happening? And we'll go over the definition, obviously, in the notes in a second. But what did I say?
The light is reflecting off of it, or I don't know, maybe that was just what the whole thing for.
It reflects off the surface. Like things reflect off the surface, but what is refraction? Is my question. Refraction.
Doesn't it like shift?
Okay, it's shifting the light rays. Very good. It's shifting those light rays. Now, as a result, when it shifts those light rays in the glass, we're going to see a bit of a staggered image. Now, oil happens to have a certain property to it. Vegetable oil. I think canola oil works too, actually. Vegetable oil has a property, and one of its properties is called an index of refraction. And every material that has some transparency has an index of refraction. And that's how much the material bends the light body. Like, does it bend it more or less than glass? Like, does light bend more in water or glass? It's based on what's called an index of refraction. So in today's class, we're going to talk about these indices of refraction. It turns out that Pyrex, which is some long chemical name, I asked Miss Myers, I'm like, what are these beakers? And I explained the name. She goes, oh, that's just Pyrex. So these are just Pyrex beakers. Pyrex glass has almost the exact same index of refraction as vegetable oil. So what's happening is the light is getting bent as it goes in, but when it passes from the oil to the glass, since they have the same n value, we're going to call it, it's an index, it's called, the lowercase n is the variable we're going to use. Since it has the same index of refraction, it bends when it goes into the glass, but then when it hits the oil from the glass, it's not changing the angle at all. The light isn't being bent anymore. How do you see things? Everything you see is a reflection of light, really. Everything. I mean, everything you see. Like you see this green, it's green being reflected towards you. When you see black, it's nothing being reflected towards you. All the colors absorbed. You see white, it's all the colors being reflected towards you. So what happens is the light's passing through the glass, and then it hits the oil barrier, and then it hits glass in the inner beaker. Then it goes to the oil in the inner beaker, then glass, then oil, then back to glass. It's like a bunch of layers. Well, if that was a solid piece of glass, like solid glass, like a block of glass, you wouldn't see anything inside of it. You wouldn't even if there was a beaker inside of the glass, if they were both glass, it would look like one solid material. That's physically what's happening here with the light. The light is interpreting this or bending in a certain way that it's pretty much the same material according to the way light reflects it. It reflects the exact same way and refracts the exact same way through oil and Pyrex. So it appears as if the Pyrex itself is not even there because the light is not bending when it hits that inner Pyrex. On the outer one it bends. It bends initially, but then it continues through the oil at the same angle it's moving. Okay, so we're going to go over these angles today and discuss with diagrams, but that's the reasoning behind that, how that works. And we're going to use some laws today to show the idea behind this and how it works. Okay, so three things. We're going to talk about when refraction occurs. We're going to talk about how light is bent, which direction it is bent, and then we're going to use Snell's law. What that is. So let's take a look at refraction first. And what we see here in this diagram, okay, what we're going to see here in this diagram is that light, let's look at the one on the left first. So light is coming from the air, so it's traveling through the air, and it hits the glass barrier. And it goes into the glass, and instead of passing right through, right, so watch, if I continue this ray, it would look like that. Agreed? Here's the incident ray coming in. This is the reflected ray coming off. This is the refracted. Okay, I'm talking about all the red lines. Ignore the black line I drew. The black line I drew would be, assume the ray did not get refracted or reflected, it would continue in the direction it was moving. Just like what happened in that example, actually. That demo right there just did, the light going through, it passes at the continuous or the same exact orientation that it was moving. So you wouldn't have any refraction between the vegetable oil and the inner beaker. That's why we didn't see it. It disappeared because of this. Now, if something hits just glass, though, or just some material, it's going to bend. It's going to bend toward the normal, or it's going to bend away from the normal. What's the normal again? What's the normal? Because the last class, I think, forgot what the normal was. Pat? Yeah, that perpendicular dashed line right here. Remember, this is the surface. Normal force is always perpendicular to the surface. So remember that when I say to the normal is a line drawn perpendicular to the surface. So what we're noticing is that the light ray, follow my arrow, I'll point, goes through air, it hits the barrier, and then it bends toward the normal. Notice this is where it should be, but it bent over to here. That's toward the normal. That's what that means, literally. Toward the normal. Now, which angle is bigger? Theta I or theta R? Just take a look. Theta I or theta R? Theta I? How can you tell? I mean, besides just inspection? Okay, so inspection. So besides just looking, though, is there an easy way? Like, watch, do this. Think about it this way. Isn't this, right, I'm going to draw an arc. Look at the arc I just drew in. God bless you. See this arc right here that I just drew in? Isn't that arc vertical angle with theta I? Remember vertical angles from geometry? Two lines that intersect have vertical angles that are congruent. So those are congruent. And those are also congruent. So as a result, this little arc I drew in right here, well, that's the same thing as theta I, right? Take a look. This is the normal. This is the light ray. So this angle here is vertical angles of this angle up here. So if this whole thing is theta I, then theta R must be less than theta I because it's a component. Right? This might be, give me a number for theta I. A reasonable number.
30.
30? Yeah? Agreed? 30? Is that cool? I think it's a little bigger, but I'm going to leave it at 30. So let's say 30. Pick a number for theta R that's smaller than 30. 20, 14. It's probably, in this diagram, it looks like probably like half, so I'll go with 14, just think it's probably like half.
1.275.
I think it's more than point, whatever that is, away. I'm going 14, just for the sake of it. Again, random numbers I'm picking, but the idea is this. The angle of refraction is smaller than the angle of incidence for the example on the left. What about the example on the right? What about the example on the right? What about the example on the right? What do you notice? Victoria?
Are they're not equal, are they? No. Is R, no?
Not equal for sure.
Okay.
So what do you think is going to happen?
Is R is going to be smaller?
Yeah, so in the second diagram, where it went from glass to air, the incident angle right here is definitely smaller. Josh, Pat, focus. The incident angle is definitely smaller than the refracted angle at the bottom here. Okay, this is much smaller when we're going from glass to air. Now, let's talk about why. Let's talk about why these objects, or these media are bending light. When light travels, when does light travel the fastest? When? For instance, what do we say? The speed of light in a vacuum. That's the term you always hear, right? In a vacuum, there's nothing that's disturbing the flow of light. So it travels at 3 times 10 to the 8 meters per second. It travels at its maximum velocity in a vacuum or in empty air, really. Give me 30 seconds. Let me get to the end of the statement. So it's traveling really fast in air. It hits glass. What does the glass do? What does any barrier do to something? Does it speed it up? It slows it down. Yeah, it's got to stop it or slow it down in some way, right? Impede the velocity or impede its motion. So what's happening is this. The wave fronts are staggering and they're slowing themselves. So what you see here is that these wave fronts slow down and you're getting this bend toward the normal. So what I want you to write down is that in air, it's traveling fast, we'll say. These are relative terms, not numerical, okay? Fast. And then in glass, it's traveling slow. Just relative terms. But then when it goes from glass, which is slow, to air, which is fast, we noticed that the opposite happened. The opposite happened. So what conclusion, guys in the back, if I see giggling and stuff that you're looking at your iPads, I'm going to get really pissed. I'm going to move you to the front. Focus. If I see that what conclusion can I draw from this? That when it goes from fast to slow, it bends one way, and slow to fast another way. What can I write? What kind of a statement at least? Ed, give me a statement.
Well, the reactions are inverse, I guess, or the opposites.
So give me one of them. So describe what's happening on the left side diagram. As the light, give me a statement.
As the light, when the light is fast, it's reflected slow, I guess, or
Oh, give me more like when it travels from a fast-moving medium to because you're going from air to glass.
yeah.
So you want to start with like when it's traveling from fast, moving medium, and then it slows down, what happens? It bends which way? What was the phrase we used a minute ago? The ray should be over here, right? It should have passed through like this, but it bent toward the, what is this?
Normal.
Yeah, so let's write that down. When it goes from a fast-moving medium to a slow-moving medium, it bends toward the normal. This is a generalization that we're making that is true in all cases. Mike, if you want to use the restroom, you can. Okay? And vice versa. So below that, what are you going to write? When it moves from slow to fast, it doesn't move toward the normal, it moves away from the normal. So on the right here, I'm going to jot down the following. Theta I, in this case, is greater than theta R. But in the bottom, what happens? Yeah, it's the reverse. Okay? So in the first case, when it travels from air, something where it goes fast, the fastest medium we're going to look at is air. So whenever it travels from air to water, or air to diamond, or air to glass, or air to any transparent media, it must be slowing down, therefore bending toward the normal, and as a result, the refracted angle will be less than the incident angle. And the opposite is true when it moves from slow to fast. It moves away from the normal, and therefore the incident angle is less than the refracted angle in that case. R stands for refracted. Write that down. It's not reflected. I can't tell you how many people confuse that. If I use the term theta R in multiple choice, you need to know that is the refracted angle, not reflected. Reflected is always the same thing as the incident. We talked about that last class. If the ray comes in at 30 degrees and it gets reflected, it goes out at 30 degrees. That's simple. They're always equal. Refracted, it depends on the medium itself. How fast light can travel through that medium indicates the angle that it will be. Okay? Any questions on this so far? There's a lot going on. Okay, but the general conclusions you come up with are what's really important for these, right? These are your theoretical ideas, your concepts that you need to be writing down. Let's talk about something now. And remember I used the term index of refraction before for the oil, and I said the Pyrex and the oil have the same N value, or index of refraction. N, or the index of refraction, is really a ratio that compares the speed of light in a vacuum to the speed of light in the given medium. In the given medium. For example, the speed of light in water is 2.2 times 10 to the 8. But the speed of light in air is 3 times 10 to the 8. So if I wanted to figure out the index of refraction for water, just put H2O, whatever, it's going to be the speed of light in a vacuum over the speed of light through water. You don't have to have this memorized. I happen to know this. Okay, you don't have to memorize this. But that's the idea behind it. So what are you going to notice? What do you think about this ratio? It will always be what? There's two answers to this that are right. The ratio will always be what? Fill in the blank. Let's make this Jeopardy here. What is?
What is it? Proportional or something? I don't know, it's like one goes. Oh, no, well, okay, yeah, I don't know, I just.
It's not proportional. I think I like the idea, again. Keep going.
Above one?
Yeah, why?
Because,
Why is it always greater than 1? Paul's right. You know, answer that follow-up?
well, because nothing can travel faster than the speed of light in a vacuum, and we're using the problem.
That's exactly it. The numerator is the speed of light in a vacuum. You can't travel faster than that. So can the denominator ever be bigger than the numerator? No, it cannot. The denominator value, when you calculate the n value of a given substance, will always be less than 3 times 10 to the 8. So as a result, when you have a bigger numerator, right, a big numerator and a small denominator, it's always bigger than 1. If the numerator is greater than the denominator, the fraction is always greater than or equal to 1. Okay, so n will always be greater than 1 for all substances on Earth. Okay? Obviously, index of refraction in space is just 1 because it's empty air. Right? It's just 1 itself. I'm putting greater than 1 because even air, and you're going to see in a minute, is 1.000293. It's pretty much the same as a vacuum in empty space, but it's not. So there is a small variation or deviation. You can never surpass the speed of light, so as a result, that will always be true. Second blank. Who knows the second one? So the answer for this is 1.33, by the way. That's the n value for water. So the n value will always be, hold up the first part, greater than 1. What's the second part? This is tougher. Not everybody picks up on this. N will always be, anybody else? Oh, I saw another hand. Anything to say with the second part?
It'll be decimal.
Not necessarily. I mean, I guess, yeah. I mean, it could be 2. It could be evenly 2. It could happen. So I don't want to say that. Something not about the numerical part of it, though. Think back to force of friction, right? Remember Ff equals mu Fn? Remember that formula? So how do you solve for mu? What do you do? Ff equals mu Fn. How did you solve for mu? You divide it by Fn. And you got Ff over Fn. That's what mu is, right? It was a force over a force. Here, what do we have over what? Speed over speed. So, what can you conclude about the answer? When you divide a speed by a speed, like when you divided a force by a force to solve for mu, it was something about mu that is similar to this. No units. No units. Bless you. Okay, no units here. So we notice we have meters per second over meters per second. So all n values are inherently unitless. Another reason you might know it's unitless, usually when you hear a ratio, right? The definition of this was a ratio between the speed of light in a vacuum and the speed of light in a given medium. If you hear the word ratio, traditionally it means you're looking at two numerical values and how they're related to each other, not their units. Usually when you're talking about a ratio, units cancel out. I shouldn't say always, because some books will use the word ratio and units will drop off. But really the definition of something that's in a ratio, they should have the same units and you're comparing their magnitudes, their numerical quantities. All right, let's take a look at a table. So this is a table that either you will be given on the test, you don't have to memorize it, or I'll tell you in the problem that specific materials index. So if the problem is talking about, polystyrene right here, I'll tell you it's 1.49 in the problem, or I'll give you the table and I'll make the name of it, you have to find it in the table. Maybe there'll be a problem, which you're going to see at the end of today's lesson, where you have to solve for n, right? Given values, you have to solve for n based on measuring the angles, and as a result, you can figure out what the material is. Okay? Now, what do you notice? What do you notice? Anything about this? Anything about this? What are some things that pop out? Give me something. It's always measured good at STP, standard temperature and pressure. Very good. So we're looking at, for solids and liquids, 20 degrees Celsius. Gases, we're looking at 1 atmosphere because the pressure affects the gas. So we're assuming that those things are held constant. Very good. What else? What are some other things you notice? What do you notice about some N values? Good.
Oh, I
Oh,
noticed that,
something else.
more than Miller, I noticed that even though ice is a solid, it's measured at a different temperature because of the freezing point.
Good, that's true. Absolutely, Jake. Good point. Ice is measured at 0 Celsius because it's got to be 0 to be ice.
I was just gonna say a lot of number, like 1 or right around 1.
Yeah, 1 and then maybe 2, a few of them, right? But you notice that some of them are pretty close to each other. Again, for Pyrex glass, it's 1.47. For vegetable oil, it's 1.469. That's why you did not see the Pyrex glass. So where's, I don't even know if there's regular glass on here. Pyrex is not even listed as one of these, I don't think. No. Pyrex, the chemical name is like bi something, something, something. But it's a long name with the prefix of bi, so it's not one of these. Anyway, the idea though that some of these are similar to one another is very important. You know where it's important? In forensic science. In forensic science, if you want to know what a fiber is made of, so you're at a crime scene, and I started talking this last year with Mr. Joseph, sorry, I learned a lot of stuff. Imagine you're at a crime scene, let's say a crime took place in an alleyway. It was a shooting, a struggle, somebody got thrown up against the brick wall, punched, eventually somebody got shot, and they're trying to figure out who was the person that got thrown up against the wall because they did the shooting and then they got away. What might they look for at the crime scene? What are some of the things they look for at a crime scene?
They would look for someone with a halo.
A hair. Okay, what else?
I like where the blood lands.
The angle the blood landed, the trajectory, the shape of the blood droplets to see where it angled landed.
Maybe if a bullet was shot into a wall, the angle from which the bullet was fired.
Perfect. If the bullet going into the wall is at a given angle, you can determine the angle it hit the body, the angle it exit the body, all this. What else? There's one thing I'm thinking of that would help with this. Anything that you can think of for fraction groups in general. And what could you see on the wall?
Well, there's any fibers left in the wall.
Yeah. That's exactly what we're looking for. Fibers from clothing. So think about a brick wall. If you get pushed against the brick wall, which is abrasive, and you get like thrown up against it, there's a good chance that some fiber is going to come off. You might not think about this, but honestly, one fiber will most definitely come off your shirt if you're thrown up against a brick wall. Now, that's called transfer evidence. It's evidence that like comes off in contact. So if two people are walking past each other and they hit past each other, ever on the train you get like a piece of hair on your jacket, you're like, whose hair is this? And it's not yours, you're like, it's transfer evidence. That's all it is. I mean, really. So what they'll do is this. They'll take the fiber and run a bunch of tests to determine what it's made of. Is it polyester? Is it cotton? Is it some synthetically made of? Is it rayon, which is like spandex? What is the material made out of, right? Here's how they can test it. The N values, the indices of refraction of these materials are known. They're in a table. You can research them. Now, what scientists will do to make it simple is they might submerge that object, that material, in different fluids. Okay? And depending on the fluid, and the fluids that you'll submerge it in have a range of values. Depending on the fluid in which it becomes most transparent, like the Pyrex glass did, its N value is closest to that quantity, which can narrow down the type of fiber it is. You can also do what's called a burn test. But a burn test, what does it do to your evidence? Burns it. So that's like your last test you would do, and that's if you usually have more than enough evidence, more than enough like sample evidence in this crime scene. So this is a very useful technique using the index of refraction. And in forensic science, remember how you looked from above and you saw like kind of the shape, that like circle from the Pyrex on the inside? That little shadow, that kind of halo you saw is called a Beck line. And if the Beck line is inside versus outside, or inside of the material versus outside of the material, it tells you whether or not the N value is above or below that material. So if the Beck line is outside of the material, for example, it may be an N value above the N value of the given. So say the Pyrex is, or say vegetable oil is 1.469, and you put a fiber in, and you see that shadow, that halo on the outside of the fiber, when you're looking at a microscope to do this. You would see a shadow on the outside, it would indicate that the N value is either above or below. I forget which way it works, it's one or the other, the direction. Let me finish the statement, please. So the location of that shadow or that halo indicates the N being above or below, so you can narrow down the type of fiber it is before performing more tests on that fiber itself. Okay? You want to take like a 2-minute break real quick, grab water, come back? Okay? We'll continue with this next slide. So, what we're going to do next is we're going to take a look at a law, and this law relates the angle of incidence and the angle of, refraction. And it's called Snell's law. Okay, it's Snell's law. It was derived empirically, meaning it was derived using experimental data. Then it was shown that it was true for all substances that are transparent. So, what we're going to see here, what we're going to notice, is that the I part on the left-hand side has to do with whatever it comes from. Ni is the index of the first medium. So if light is traveling from air into glass, just those two things, air would be the incident medium, so 1.000293, whatever it was for air. And then Nr would be the glass value, which I think in the table was like 1.5 or something like that. So what it's doing is it's relating these two different parts of the light traveling through different medium. So let's take a look at an example of how we can use Snell's law. Okay, so let's take a look and identify what we can do. Mike, why don't you read it for us, nice and loud.
Snell's law gives us the...
Next one, Mike. I just went to the next slide there.
A light wave traveling through air strikes a flat, smooth surface made of fused quartz at an angle of 25 degrees to the normal. Determine the angle of refraction.
Thanks, Kevin. So it goes through the air, it hits this interface, right? The normal continues down, obviously, like that. And now we know it goes into fused quartz. Remember, anything going from air to something else has to slow down, so it's going to bend toward the normal. So it's going to be an angle like that. Smaller than 25. I already know that my answer has got to be less than 25 degrees. Okay, I don't really know what it is, but I have this statement on the side. I know that the incident angle coming in itself is indeed 25 degrees. It is 25 degrees. So what we're trying to figure out is, what is the value of theta r in this problem? What is the value of theta r? We know it will be less than 25, but we don't know what it actually will be. So let's go ahead and use Snell's law. Let's write down what Ni and Nr are in this case. So the incident medium is the first medium. So what is it coming from? Where? Air. So Ni is the N value for air, which is really just 1. We can write 1.000293 if we want to be really precise. But in your calculations, for air, you can just use 1. Okay, for your calculations for air, all you need to really do is use 1. So if you don't want to even write these for now, you don't have to. So air is 1. What is fused quartz index of refraction from your table on the previous slide? What do you have for fused quartz? Fused quartz. Victoria, what do you got? 1.458. And since fused quartz is down here, the second medium, that is the refracted medium. So we've got the N for air as Ni, the N for fused quartz as Nr. The incident angle is the angle it hit from the air, 25 degrees. We want to figure out what the refracted angle is. We know this is true, but we don't know what the value actually is. So let's go ahead and write Snell's law. Okay, let's go ahead. I can ignore the rest up here because I have everything written down. I don't need the diagram anymore at all. Snell's law, Ni sine theta I equal Nr. Whoops, let me use the parentheses the same way. Nr sine theta r. Now, you don't really need the parentheses, folks. Okay? You don't really need them there. Simply because this is multiplying. I'm just putting parentheses so you know that sine of theta is some number. Like the sine of 30 degrees is 1/2. The sine of 60 degrees is 0.866. It's a number, it's a quantity. So you know theta I. So this is going to be sine of 25. It's a number. Ni is 1. Nr is 1.458. But our problem here is to figure out what is theta r. For the sake of this, let's plug in numbers. We'll solve this algebraically a little bit later, but let's do just plugging in numbers for now. So that's a 1. And we've got sine of 25 degrees. Make sure, again, you're in degree mode. You can be in radian mode when you're in math class, but in physics, everything's in degrees, not radian. So make sure you're in degree mode. All right, and here's what you get. I'm literally just plugging in the numbers. That's all I've done so far. 1, which is the index of refraction of air, times sine 25 equals 1.458 times sine theta r. Divide by 1.458, please. Take sine 25 over 1.458. What do you get, please tell me? Again, divide both sides by 1.458. I know it's going to be a decimal because I'm taking sine of 25, which is a decimal, and dividing by 1.458, which is greater than 1. So a decimal divided by a number greater than 1 will remain a decimal. What do you get? 0.229. Give me 4 decimals, just because we're going to have to do a little more work.
0.2897.
Okay.
No.
98?
99.
99. All right. So if we round to 4 decimals, that's what we get for sine theta r. Now, in your math class, you have not gone over this yet, but it's a very simple technique to solve for theta r. This is clearly not the angle. An angle of 0.2 degrees as a result of an angle of 25. That's a huge bend toward the normal. This is not the angle. This is sine of the angle. We want the angle. How do you get rid of sine? You've done this before? Okay, because you didn't do it in Mr. Hall's class, yeah, right? Do you remember how to do it? Yeah.
You do the sine
Oh,
and then you times it by 0.2899.
Guys, come on. Please listen. She's explaining. You do exactly what Jenny said. You take what's called the sine inverse of both sides. So if you want to get rid of something, normally you think like, okay, sine is like multiplying. It's not. But it's like sine times theta. It's not really, but it's like that is. You would divide by sine. When you divide, it's really multiplication by the reciprocal. And reciprocal, another word for that is inverse. So if you want to remember that what you're doing right now is called the inverse sine. So you need to do this. You need to take the sine inverse of both sides. And this is weird. I know it's not something you've seen. And I'm just going to teach you the method. You're going to try it on your calculator and you're going to make it work. You're going to see that it works. But you're not going to go into much detail right now. You're going to see this in your math class a lot more. But you already have an idea, which is good. So when you do a sine inverse of sine, what happens when you do a function and its inverse? Anybody remember? They cancel out. You've done compositions. I know you've done these. You've done f of g of x, right? If g of x and f of x were inverses, and you did f of g of x, the answer is always just x. Just x, or whatever is left. So sine inverse of sine, you're just left with whatever's here, which is theta r. So on the right-hand side, you have theta r. The left-hand side, you literally have this. So you go to your calculator, make sure you're in degree mode still, and you got to pull up what's called sine inverse. Well, how do you do that on the calculator? What do you press? There it is, Mike. Very good. Second sine. So press second sine on your calculator. Press the second command, then hit the sine button. Then type in 0.2899 enter. What do you got?
16.85.
16.85. Nice, Mike. And what we know is that it's reasonable. Mike, can you tell me, Pesh, sorry, Zeus, yes. Mike, why is it reasonable? Why is this reasonable as an answer? What was the statement we made in the beginning? Scroll back up in your notes. Look at the statement we made in the very beginning of this problem. In the top right, what did we say? Yeah, remember, why did it have to be less than 25? Why did the answer have to be less than 25? Because you're going from where to where? You're starting in what material? air and you're going to quartz. If you're going from air to anything, it slows down. When waves slow down, they bend toward the normal, and therefore theta gets smaller when you bend toward the normal. You're making theta smaller. So the answer had to be less than 25 because we started with an angle of 25, so we can at least say that our answer makes sense. Okay, it makes sense. Let's finish with the last. A light wave travels from air to an unknown material. If the angle it hits the material at with respect to the normal is 30 degrees, and the angle of refraction is 12 degrees, determine the material that it passes through. So let's list what we know. We know that it's starting in air, so what's Ni going to be for air? Good. Starting in air, and N of air is 1. We don't know what it's ending in, so we don't know that, and R, because we don't know the material. What about the angles? What angle does it hit with? It hits with 30 degrees, and the refracted angle is 12 degrees. Good, I'm hearing people saying them lightly though. Okay? So our goal is to find NR. That's easy. Use Snell's law. Good old Snell. So I've got 1 times sine 30, which happens to be 1/2, equals NR times sine 12, which I have no idea what that is. There are certain angles you're going to pick up on that in math are ones that you will know over time. 30 is one of them. That's why I happen to know that. What do you get? So you have, this is 0.5 equals NR times sine 12. I divide both sides by sine 12. And what do you get for NR? There's no need for inverse here. Remember, we're not solving for theta. We don't have to do that inverse thing again. Just literally type this in, sine 30, which is 0.5, over the sine of 12. 2.4. No units, obviously, because it's the index of refraction. So what material is it? Go back to your table. What material would this one be? Yeah, this one would be diamond. Okay, the next closest in the table is cubic zirconia. And cubic zirconia is 2.2. Why do you think knockoff diamond rings are made with cubic zirconia? It has to do with the index of refraction. The index of refraction is what causes sparkling. And I'll talk about that in 15.3, how sparkling actually occurs in a diamond. Okay? It's a phenomenon. It's actually kind of cool. But that's why cubic zirconia is used as a knockoff. It's traditionally the same color. It's rather translucent, clear, no colors to them in general. Although some diamonds have colors. I told the other class, I went diamond digging once. Anybody been diamond digging before? I was somewhere near Colorado. I forgot what state I was in. We were driving across country and we were camping somewhere. And we were at this crater, like a site where like a meteor hit a long time ago. And there were diamond deposits. And you could pay like $10 just to dig all day. You can keep whatever you find. So you had to dig, put it through these sifters, sift out like pebbles, put it through water to like clean it out, and then you use what's called like a sloshing. It's like this trough that's filled with water, and then you like try to find the diamonds. We didn't get any. One guy found 3, but they were like so small that they weren't worth anything. Diamond needs to be big enough to be cut, to be placed on like a jewelry or like a ring or earrings or anything. It needs to be a big enough rock that it can actually be cut at a certain angle. So small diamonds are worth like $2. They're worth nothing because they can't actually be mounted on anything. You put them on pendants usually. Diamonds that can't be cut that are like, because when you get diamonds, they're not cut, they're not like at angles. A diamond you don't pull to the ground, it's like, oh my gosh. A diamond is like smooth and it's like an egg. It's like an ellipsoid. It's the shape like an egg. Okay, so it has to be cut, it has to be big enough. So it's not the way it is. So if one can't be cut, usually they get mounted with pendants. So I never found any that day. But you can go diamond digging, and diamonds, the colors are not all clear. They're different hues of like a grayish, brown, yellow. That's the colors you're going to see for diamonds. But cubic zirconia is so close to it that it's used a lot. Homework problems, okay? They're mathematical, I think, mainly based on just Snell's law. And I think one of them you're calculating an index of refraction.